Okay, I'm going to try to do a video here that's an introduction about time series stuff, and I'm going to try to do it so that it is broad enough to apply to more than one audience. So please bear with me here. So I'm going to start with a very broad intro. So things vary in the sky. A lot of people don't necessarily appreciate that, but of course the word planet, it comes from the ancient Greek word that means wanderer. So things are rotating, orbiting, and revolving. There's lots of things that change. Stars move around within the galaxy and they orbit the galaxy. Stars themselves have spots and flares and coronal mass ejections, just like the sun does. And the young stars that I like to study, they have even bigger spots than the sun does, bigger flares, bigger everything, and they rotate very quickly. And all of these things are related. And it turns out that very young stars can accrete, but so can old stars, because very old stars can sometimes produce dust in the outer layers of their atmosphere. And white dwarfs, even, it turns out, can have dusty disks and can accrete from their disks. So there's lots of variability at from stars of all ages. So when we're talking about periodic variability, sometimes it means orbits, like moons, asteroids, or comets that are on recurring orbits, our planets or other planets, binary stars orbiting each other. You can also get pulsations because stars ring. Stars of all sorts can pulsate. Sometimes the most basic kinds of pulsations that you may have read about in Astro 101 is something called opacity-driven instability strip pulsation. So that's the thing where the star cools off and condenses a little bit, which then causes certain elements to recombine, which then means that the opacity increases, which means that the energy is held in and it heats up so that it expands, and then it cools off and the stuff recombines and then it collapses. So you get an opacity driven, the opacity changes, which causes the star to puff up or collapse. And so you end up with this kind of instability strip puffing up and collapsing pulsations. This is the kind of not wolf way, it's the kind of RR Lyrae kinds of pulsations. But you get smaller pulsations on stars of all sorts because this entire field of helioseismology or astroseismology, note that it's not astroseismology because the prefix and the suffix have to match. So since seismology is Greek, it has to be asteroseismology. Stars ring like gongs. So they ring, and you can learn all sorts of really interesting things about the structure of the star when you study those kinds of pulsations. So all sorts of really cool things you can learn from the pulsations of stars. And the kinds of things that I study is rotation. So when you have spots, either hot or cold spots, rotating on the surface of the star, rotating into and out of view, you get a periodic signal. You can also get things that are periodic from dwarf novae, where you have like a white dwarf and a giant companion. And as the two orbit each other, you can get regular accretion from the giant on the white dwarf. You can have also periodic things on much longer cycles, like the solar activity cycle, like every 11 years, you have changes in the amount of spots that the sun has. So you could do all sorts of interesting things with the periodic cycles that you find. And it starts, of course, with just simply identifying the period, but you can also identify the amplitude of the signal, the shape of the signal, even the color of the variations that you're seeing. And you can use all that information to try to disentangle what is varying and why. There's, of course, tons of aperiodic things as well. Flares, novae, supernova, mergers of compact objects, explosions really of any sort. Often accretion onto anything is aperiodic, by which I mean black holes, neutron stars, white dwarfs, young stars, FUORs are catastrophically accreting young stars. All of those are accretion. You can also have lensing, so like microlensing, gravitational microlensing, or large scale gravitational lensing, where it happens just once and that's all you get. You also can get asteroids or comets visiting the inner solar system, and sometimes they come on a one-way trip. So all of these things happen only once. So you can do different things with these aperiodic things. You have to find them. If you find them, you have to quickly follow up. And in order to understand what's happening, you need to get those follow-up observations, usually from more than one telescope, to try to understand what's happening, to follow the shape of the variability, follow the amplitude and the color of the variability. Sometimes it's even hard to figure out exactly where the variability is coming from to try to understand what is varying and why. So realistically, in the context of the kinds of projects that I do with you guys, it's usually young stars varying due to spots or accretion or occultation by the disk material, the circumstellar disk material. Sometimes we can find one-off occultations, but usually if we find those kinds of excursions, it's more likely to be noise. We find lots of binaries. We find lots of background giants. We find lots of flares. We find lots of things that are long, slow variations that we can't always figure out why it's doing that. We just see the long, slow variations. We find lots of cosmic rays hitting the detector. In general, we're not going to be finding planets just because in order to find planets, you need really, really precise photometry and precise data reduction routines, and the kinds of stuff that we're doing is usually not that precise photometry. All right, terminology and the kinds of infrastructure. So when I say light curve, I mean brightness as a function of time. That could be measured in flux, it could be measured in magnitudes. Sometimes I abbreviate that LC for light curve. That can be confusing in this context because sometimes LC means long cadence. What is cadence? Cadence is the rate at which the thing is observed. In other words, what is the time step between adjacent observations? This is important because the light curves may or may not be evenly sampled. In fact, it's pretty rare in astronomy that it is evenly sampled. So sometimes you can say, yes, I observe this thing every 30 minutes, but sometimes it's not that straightforward. Sometimes it's, well, about every 2 hours, right? That's why sometimes you use the term windowing function, meaning here's the set of times in which I observed this target. So cadence isn't really the right term, but windowing function is. Time sampling sometimes is also used. The period is the length of the repeating cycle, typically abbreviated P. LS is Loam-Scargill. That is a method based on Fourier transforms of looking for the period. I'll talk more about that in several slides from now. When I use the term folded or phase folded, that's when you take the light curve and you can imagine sort of like an accordion folding it back on itself. You plot the brightness as a function of the fraction of period, not time, but phase, fraction of the period. All right, so in terms of the cadence, the rate at which you sample affects what you can see. So if I sample the target only once per month, it's exceedingly unlikely that I will be able to find periods that are days long. If I sample every hour, though, I will easily find periods that are days long, but I probably won't find flares that are seconds long. But remember that irregularly sampled data is the norm in astronomy, and it actually is really helpful in terms of finding these different timescale things. I'll show you examples of that later in this slide collection. It turns out that really big gaps in the data stream does very strange things to the math, and we'll talk more about that later. Now, the time series analysis that we have, the tools that we have available. If you look up in like your the kinds of textbooks that you have in, available in your analysis classes, even in college, the kinds of tools that you get taught in those contexts usually assume that you have long, unbroken, evenly sampled measurements of comparable quality. In other words, the error bars are comparable in all of them. And those tools were developed for people like physicists in labs or in medical physics, where you have those long, unbroken, evenly sampled data sets, like an EKG or an EEG, where you get to control how you take the data. So you can do that. But in astronomy, we don't usually have that. We don't usually have long, unbroken, evenly sampled measurements because things rise and set. Objects move behind the sun, instruments break, weather doesn't cooperate. Satellites, even if you have satellite data where you don't have to worry about, the sun coming up and needing to close the telescope dome, satellites still need to call home and download data. And moreover, not every point has the same size errors. And if you're working in X-rays or gamma rays, you're counting individual photons. So not every point, definitely every point does not have the same size errors. So astronomers have developed a huge number of specialized tools to deal with these unevenly, irregularly sampled data sets that have varying signal-to-noise levels. So when you run into time series analysis in all of your college courses, even applied math, they're not going to tell you about these tools because astronomers have reality-based needs. So we've developed our own tools to deal with this. All right, so here I have something, brightness as a function of time. Is this variable? I'm going to add some error bars. Is this variable? What about that? Is that variable? What about that? Now I've got different size error bars. What about that? Now they're not evenly sampled. So there's many different tools you can use. RMS, the root mean square, is defined like this, where the n is the number of points and the x's are the values of the individual points. Sometimes RMS is just called sigma. And what this is doing is just looking at the scatter in the light curve. It's looking at how it compares to a straight line, a flat line. But this all by itself doesn't tell you whether or not it's variable. It's just telling you how much scatter there is. Sometimes this is useful to use in context with all the other tools that we have. Standard deviation is a lot like RMS, but it is subtly different. The variation is given by this, and the standard deviation, which confusingly is often also called sigma, is the square root of the variance. This also explores the scatter in the light curve. It is also independent of the error bars. I use this a lot in what I do. The chi-square test. All right, so what this tool is telling you is if you assume that the object you're studying is not variable, in other words, a flat line with time, then are the variations from that line significant? So in this expression, n is the total number of points. This sigma is the error on each individual point. Sigma, this term means sum over all the points between I and n. And this is the individual magnitude, and this is the mean magnitude. So if you calculate this chi-squared, if you get a large number, it is more likely to be variable. This is taking into account the individual errors on each point. And even though I've written here magnitude, it does not matter if you are working in flux or magnitudes, you can still calculate this. And you can do this if all you have is one band observations of your target. This is independent of time. It is independent of your time sampling. And what range matters, in other words, what your threshold is for is this variable, is this not variable, depends entirely on your data set and what size of errors you have. I use this a lot. So now for those 4 plots I showed you earlier, here are the chi-squared values. For this, chi-squared is 0.33, and I don't think you would get any argument from anybody that this is not variable. This, I get a chi-squared of 8.3. That's more of a borderline case. For both of those, it's the same error bar sizes, just different sampling times. And since chi-squared doesn't depend on the sampling time, both of those result in a chi-squared of 3,350, and that's variable. Here's some real data. So this is brightness as a function of time. This chi-squared turns out to be 1.13. It is not variable. I didn't plot the error bars here, but look at the range of that, 14.8 to 14.7. Look at this one. It goes between 14.8 and 14. The chi-squared here is 110. That is variable. All right. Now, if you are lucky enough to have 2 channels, 2 bands of the same source taken at more or less the same time, this is something developed by an astronomer for this specific case. Now, the math looks horrible, but it is not. This is called the Stetson index. It is given by this, where these p's are defined by this, and the deltas are defined like this. So n is the number of pairs of observations taken at the same time. P is the product of the normalized residuals of the two observations. G is the weight assigned to each residual. Often people just set that equal to 1. SGN is an operation. It just means the sign of the value, because you can't take the square root of a negative number and still be physically real. So that's why it's got this operation. Sigma, in this case, is the error on each point. After you do all of this calculation, if you get a larger number, it means that your object is both more likely to be variable and the two bands you have are correlated. In other words, the two light curves taken at the two different filters are correlated. So if you have two bands of data that are uncorrelated, you're not going to find it. But astrophysically, if I have, say, two bands from ZTF at G and R, those are two optical bands that are pretty close to each other. And I don't know astrophysically how to make something vary at G but not at R. If I have two bands from NeoWise, WISE 1 and WISE 2, I don't know how to make it vary at WISE 1 but not WISE 2. So if you have two bands that are close to each other, they better vary together. So Stetson is pretty powerful, because if you've got two bands that are close to each other and the two bands are correlated, they're probably variable. However, if there is correlated noise, if you have the same instrument and for some reason, electronic or otherwise, if there's correlated noise, you can be fooled by this metric. But I use this if I have two bands because it's super powerful. So here I have brightness as a function of time. The open circles are IRAC 2 and the solid circles are IRAC 1. The additional colored circles means that the observations have been paired. So in this case, you can see that the dips and wiggles, so in order to make it on the same plot, the 3.6 is plotted at the true value, but the 4.5 microns has been shifted to show up on the same plot. But you see when 3.6 goes down, 4.5 goes down. When 3.6 goes up, 4.5 goes up. Up, down, up, down. Stetson here, the index is 11.3. So this is both variable and correlated. Here, though, same notation. Here we've got 3.6 going down, but 4.5 doesn't go down. Here we've got 4.5 going up, and 3.6 has gone down. Here too. So here Stetson is 0.21, not correlated. So how do you know what to take as variable? Well, you need to play around with the statistics for every object in your collection, and then you have to look at the distribution of the statistics. You have to look at the light curves that go with that metric, and you have to do a little bit of experimentation. You have to decide what is variable and what is not variable. You may need to make some synthetic light curves. You need to make some synthetic light curves, maybe even add noise where the properties of your synthetic light curve noise matches the noise properties of your real light curves, and then decide where you're going to set the line. No matter what you do, you're going to lose some legitimate variables and you're going to end up keeping some non-variables no matter what. But you have to decide where that trade-off should be, whether you want to be absolutely certain that everything you have reported as variable is variable at the expense of losing variables, or you want to be absolutely certain that you're catching all the variables at the expense of including some non-variables. You have to decide where that trade-off should be. It's going to be completely different for each data set you have, because it's going to be depending on your observing cadence, the photometric properties of the instrument, whether or not you have more than one band, and what kinds of things you're observing. Like if you're looking for explosions, you're going to do different kinds of statistics than if you're looking for stellar rotation. And of course, if you're looking for, planets, you're going to do something totally different. So you have to make these judgment calls depending on what kinds of data you have and what kind of science you're doing. So the next several plots are an example of what I'm doing for exactly that process for YSOVAR, which is a data set that I have, which was using Spitzer data in 2 IRAC channels. of young stars. And so this is the RMS statistic from several slides ago as a function of brightness, I1 and I2. And we had a dozen clusters. So this is all of the clusters except Orion. This is just one cluster, and this is just Orion. So this structure here, the RMS is curving up here because the sources are just getting fainter. So the scatter is getting worse at the faint end. But look here. Do you see how you get all of this scatter here that's happening at the bright end? Those are the young stars. Those are all the young stars. So those are the variables. Now, here's Stetson. Here's the distribution of Stetson as a function of brightness. Here's the whole distribution, and then this lower panel is zoom in on the distribution from the top. The distribution is hugging zero, especially near the faint end, because there's much more random noise at the faint end. It means it's not correlated. But at the bright end, almost everything is variable and correlated, again, because those are the young stars. So this is a histogram of that Stetson distribution, and that the distribution of that main peak is a Gaussian, and the deviations from that start to dominate at a Stetson value of 0.9. And so that's what we took as the cutoff for variable and not of the Stetson index. Then we used the Stetson index to help decide where we were going to cut off the chi-squared limit for objects for which we had only one band. So the chi-square cutoff that we took was based on the 3 sigma for the distribution of all the chi-squares. We took the chi-square of 5 as the limit. So that solid gray is the chi-square distribution for everything that we thought was variable based on Stetson. And so this is the distribution of everything that had a chi-squared. That's 3 sigma for for a fit to that distribution. And so that dashed line is that chi-square of 5 cutoff. So everything to the right of that line we took as variable. All right, so if you want to start playing with light curves, there's a lot of YS/OVAR data out there. Those examples I just showed you is what I did as part of YS/OVAR to define what is variable. The YS/OVAR is a very rich data set. It's very well sampled. I've still got a lot of unpublished YS/OVAR data. There's an awful lot that can be done with it. But you don't get to set those cutoffs because the collaboration already agreed on what those cutoffs are. So if you want to use those data, let me know. I'll give you access to the light curves I have. For the light curves we already published, those are already delivered to Ursa, and you don't need to ask me to get access to them. You can just get them and start playing with them. If you are using other data sets, though, you get to set the cutoffs. If you want to use ZTF or Assassin data, that's all ground-based small telescopes, and they have tons and tons and tons of data. But it is ground-based small telescopes, so it's noisier. And things rise and set, right? Because they're ground-based, and so the sun rises and sets every day, and it's ground-based, so it's noisier. But because those small telescopes have long time baselines, and so you can get light curves that are more than 1,000 days long, but they're noisier. Now, remember that both ZTF and Assassin, the science driver for those campaigns are explodey things, supernova, and other kinds of exploding stars. So they're not trying to go for exoplanet transits. They're not trying to go for stellar rotation. So those pipelines are not trying to go for millimagnitude precision. So you are going to have to work hard if you want to do really precise photometry. But if you want to use their pipelines and you're not going for millimagnitude precision, then you're good. So you will need to do your own analysis to decide what you think is variable or periodic, because periodic is also variable, but variable is not necessarily periodic. You will have to set those limits yourself based on the data that you have. Now, K2 and TESS, again, tons of data that's out there. The space-based light curves are super precise because those missions are specifically designed for looking for tiny, tiny, tiny dips because they're looking for rocky planets. But the background from those space missions can be really, really complicated. And the variations from the background in the images and the background from the spacecraft itself is sometimes convolved with the star variability. Like the people who write the pipelines, often they're looking for the tiny dips from transits. And so they don't care about separating, oh, that's due to the moon and that's due to the star variability. They just want it all gone. So the pipelines that they produce and the data that they deliver back to the archives, they just remove all of that. And the different pipelines have different strengths and weaknesses. So if you're looking for stellar variability, it's super useful to grab all the possible data reductions of your target. And there's going to be at least two, usually somewhere between 2 and 5 different data reductions for each target. And it's really useful to grab all of the possible data reductions and compare them because they handle the background in wildly different ways. And you might really like one over the other. And it's often not consistently like this data reduction is always the best. Sometimes other, it depends on what the background is in any one location. And for K2, the pixels are big, and for tests, the pixels are enormous. And you need to worry about source confusion. And by that, what I mean is you may care about your target, but there may be other brighter targets nearby. And when you pull the light curve from K2 or TESS, the variations that you're seeing may actually come from that other nearby star, not the star you care about. So you have to worry about that source confusion. And here again, often it is the case that you have to decide what you think is variable or periodic based on the light curves that you have. And source confusion is usually the limiting factor here. So what do you need to do for any given data set? You need to look at what you have. You need to look at the distribution of metrics. You need to look at the light curves and make some sensible and defensible choices. You're going to lose legitimate variables no matter what. You have to decide where your trade-off is. And you have to set those limits for each data set separately depending on what you're seeking, because the cadence, the precision, and the science that you're doing is going to be different, right? Even if you're looking for this, even if you're doing the same science, you may need to set different limits for different data sets. There are other ways of finding variables than I've shown here. There's many statistics out there. If it's periodic, it's probably also variable, unless you can show that the periodicity matches something instrumental. Like for example, if you're looking for really long timescale things in ZTF data, if you come up with something that's about 28 days, you might have rediscovered the moon, because the moon causes scattered light in the ZTF data. And so if you're finding something that has a suspicious non-astrophysical cause, it may be that you've discovered something like that in the ZTF data, for example. So you need to think about that when you're looking for periodicities in these data. Defining what you mean by timescale, if it's not periodic, is surprisingly hard, and there's no good, widely accepted thing to do. People are still trying to figure out what the right answer is there. But a very, very common thing that you encounter in terms of both variability and timescales is autocorrelation functions. So let me just spend a couple slides on that. The autocorrelation function is sometimes abbreviated ACF. What it's doing is it's looking for repeated patterns. So what it does is it slides the light curve along itself. So for example, we've got a light curve at the top, and I'm going to slide it with respect to each other and calculate it at each step. And the bottom there is the calculated autocorrelation function. So it's this thing, right? And so as I calculate it, initially that number is big, but then I shift it one step and that number gets smaller. I shift it again and the number is smaller. Shift it again and oh, look, things are starting to line up a little bit, like here and there and there. And so that number gets large again. So that's how it works. The difficulty, though, is that you have to linearly interpolate what the light curve is, what the light curve you have onto even time sampling before you even get started. So that's already a little squidgy. And moreover, there's arguments about the best way to interpret these results. So in the stuff that I do, based on lengthy discussions with collaborators, we take the first peak, providing that that peak was above 0.2 threshold. The reason we do that is because if the object is periodic, this recovers the period. Some people do autocorrelation against itself, but you can also do autocorrelation against the other channel. I've done this on some data, but in general, I don't find it as useful as other people do. Okay, so this is what I said. This is where it lines up initially. This is where it lines up best after the initial lag, and this is maximally not lined up. And you see the threshold of 0.2. So this is where I would take the ACF value. All right. Now, if you have two colors, you can also make time-dependent color magnitude diagrams. If you have two bands, now you have to make sure that the two bands were taken within a certain time of each other. For YSOVAR, I have the two bands taken within a few minutes. For ZTF, the two bands are taken within a day, which isn't ideal for young stars, but it's all I've got. For NEOWISE, the two bands I think are taken, I don't think it's 90 minutes. I think it's much sooner than, I think it's just a few minutes. I don't know where I got the 90 minutes, but I think it's only a few minutes. That's why the light curves I plot colored points when there's more than one filter involved so that you can interpret the time series. So for example, here we've got brightness as a function of time. And again, the solid circles are 3.6, the open circles are 4.5, but the additional colored circle means, oh, I found a pair, right? So that means that those two bands are within a few minutes of each other. This one, note, is lonely. There was only a 3.6 micron point taken here, and there wasn't a 4.5 taken. But all the rest of them have matches. Okay, so now I'm going to plot 3.6 versus 3.6 minus 4.5. It's going to start black and end up red. So it's going to start here and then wander up here and then wander down here, and it's going to end up down here. So it is a time-dependent color magnitude diagram. This is the reddening vector. So what this is telling you is that this variation that you're seeing in this star is consistent with that due to reddening. So here are the numbers for this light curve. The chi-squared is between 16 and 17 for the two bands. So it's variable because it's above 5. The Stetson that I calculated is 3.4, which is above 0.9. So this is YSOVAR data. So it's variable by that metric too. The relationship in this color magnitude diagram has a correlation coefficient of 0.87 and a 0% chance that it is not correlated. I did Monte Carlo simulations to show that. The slope is really close to that expected from reddening. So this long, slow fading that's happening here is probably due to stuff in the outer disk that is slowly moving in over 40 days, occulting the central star. So because I have two colors, I have a chance of understanding what is causing the variability here. This one, okay, chi-squared is 32 for I1 and 62 for I2. So it's variable by that metric. The Stetson is 5.3, so it's variable by that metric too. But look at this. The relationship here has a correlation coefficient of 0.7 and a 69% chance it's not correlated. But the slope is almost orthogonal to the reddening. I have no idea what's going on here. Not a clue. It gets redder when brighter. This makes no sense. I don't know what's happening here. We have a whole bunch of these. For a long time, we thought we'd screwed something up with the data reduction. I don't know what's happening. This one, chi-squared is 20 for I1, 31 for I2, so it's variable. Stetson is 4.3, so it's variable by that metric. The relationship here has a correlation coefficient of minus 0.2 and a 57% chance it's not correlated. There is no realistic or believable slope here. I don't know what's causing the variability here either. Not a clue. All right, terminology and infrastructure beyond that. Periodic time series analysis. So remember, finding planets is much more subtle and harder than what I'm about to explain. Much of the mathematical infrastructure has been developed for evenly spaced data sets, which we in astronomy do not have. The regular Fourier transform, the way that it works is for any pattern, the theory, the Fourier transform theory says you can replicate any pattern by summing up sine waves. But in order to do that, you need evenly spaced data. And that's really, really good at finding periodic sinusoidal things. And the way that this works is, again, you can represent it by a sum of sine waves. A single sine wave is easy. Two sine waves added together is a beating waveform, more complicated, more sine waves. So there's lots of web resources like, Khan Academy. But here's like the high points. This is the math. This is some of the theory behind it. But here's basically the idea. A single sine wave you can make easily. Add something in more complicated, you can get a more complicated shape, right? So you can make a square wave or a sawtooth wave by adding together sums of sine waves. So in the late 70s and early 80s, Lohm and Scargill were trying to figure out how to make Fourier analysis work for unevenly spaced data. And the Lomscargill approach is still really, really good at finding periodic signals. So the output of the Lomscargill analysis gives you a power spectrum. The way to interpret that is how much power as a function of sinusoidal period or frequency you need to recreate the light curve. It can be really messy, and you have to empirically set what the threshold is in the peaks that you want to believe. And the output then is you take that peak, as many peaks as you want, and create phased or phase folded light curves. So you take the light curve, you calculate the peaks in the Lomscargill analysis, and then you phase up the signal and plot it as a function of phase. So what does that mean? Let's first remember how sine waves are defined. So remember that you've got a cyclical motion, but the sine wave is, in this case, for example, tracing out the position on the y-axis, right? This hopefully looks familiar. And the entire sequence is between 0 and 2 pi. Half the sequence is 0 and pi. Hopefully that sounds familiar. Okay, you go to the next one. Come on, next one. Okay, so in trigonometry, you plot that between 0 to 2 pi. But now we're going to think of that as a fraction of cycle. That's phase. So you can say this is phase 0, this is phase 0.25, this is phase 0.5, this is phase 0.75. But you can also start that arbitrarily someplace else. That can be phase 0.25, that can be phase 0.5, that can be phase 0.75, and that can be phase 0. That's also totally legit because phase, whatever you call phase 0 is totally arbitrary. It's a cyclical pattern. It repeats. I can set phase 0 wherever I want. So if I have a light curve with period of 10 days, I can plot it between 0 and 1 phase. If I have a light curve with 0.3 days, I can still plot it as 0 to 1 phase. If a light curve with 2 periods, I can make 2 plots, 0 to 1 phase each. Sometimes you also see people plotting it as phase 0 to 2, which is then just 2 copies of the light curve, because sometimes it makes it easier to see patterns that way. So this is an evenly sampled light curve phased up. That is an unevenly sampled light curve phased up. This is an evenly sampled light curve, but sampled only once per day for a period that is 1 day. What that means is you're only sampling it at the same part of the light curve. And then phasing it up is impossible because A, I don't know that this is variable. So how would I know the period to use? And B, the phased, even when I know the period from some other source, it's just a dot because I'm observing it at the same part of the phase every time. Okay, here's something more complicated. This is brightness as a function of, in this case, time. Now, the sampling here is very poor. The histogram here is the steps, the time steps between. The smallest time step is 2.5 days. The longest time step is 17.5 days. But look, here's the Lomscargill power as a function of frequency. But the period is 0.01 days. And Lomscargill finds it. It finds it really obviously, and it's beautiful phased up. This is the benefit. This is the power, the magic of unevenly sampled data. If this was evenly sampled data, we would not be able to recover this. But the fact that this is unevenly sampled data, that is why, even though the closest 2 points were sampled 2.5 days apart, we can still recover a 0.01 day period because of these unevenly sampled data. It looks like magic, but it works. That's math magic for you. Here's another one. Here's an asteroid, but look at these big gaps, because in this case, this is over a long time scale and the sun is in the way. When you do the math with these big gaps, you end up with these weird harmonic peaks. That is an artifact of the gaps in the light curve, and these other peaks are not real. Only that main peak is real. This is the phased light curve. So this is what I mean by the big gaps can hurt you. And this is why you have to be careful about interpreting the periodigram. That's what this is called. You have to experiment with the different peaks and see what looks the best And in this case, that peak, that 2.58 hour peak is what works. Okay, here's some real YSO data from YSOVAR. Brightness is a function of time. If I just put this light curve in front of you, you would say, well, maybe it's probably variable, but because look at that, but you wouldn't have said that's periodic. But if you do the power spectrum, this is the power spectrum here. That peak really stands out, and it's independently coming up with the same period, 2.09 and 2.07. That's the same within error bars. It's coming up with the same period independently in IRAC1 and IRAC2. And the phase light curves looks plausible. I also, in this case, did a power spectrum, a periodic analysis of the color, but it didn't find anything periodic. I'm not expecting the color to be periodic necessarily, but though that's two independent assessments that are coming back with 2.0 something days. So that's reliably periodic. This is a space-based light curve from K2. This is amazing. Here's flux as a function of time. You can almost do the Fourier transform by eye. There's some flares in there too. Here's power spectrum, the little texture you see down there. That's not texture in the Fourier transform. That is tick marks in the plot. Here's just one sinusoidal component, and it is beautiful phased up. You don't get to argue with me about whether or not that's periodic. I know this period to 0.0001 day precision, if not better. Ground-based data don't look like this. All right, so things you need to worry about. What if some of the texture in your light curve comes from the instrument and not the object? You have to be really careful in your data reduction. What happens if you have long-term real variability onto which shorter-term variability is superimposed? Sometimes that means you need to subtract off the long-term variability, even if it's real, in order to analyze the short-term variability. To first order, if you have a campaign of X days, you can only get a period of X over 2 because you have to watch at least 2 cycles before you believe it's periodic. Okay, so with K2, the campaigns were 70 days, which means the longest period that I believe is probably 35. For tests, the campaigns are 30 days, which means the longest period I probably believe is about 15 days. For ZTF, I can have data that's 2,000 days. So you can find really long periods that way. The wildly uneven time sampling can be good, or it can shoot you in the foot. So you may need to do simulations. You may need to create synthetic light curves where you know the period because you've created the light curve. You use that synthetic light curve. You take the real time sampling you have and see if you can recover that known period. Then you can do that for a range of simulated periods to see which periods you can return. That way you can do the simulations to make sure the periods you're retrieving are real. The math magic is wonderful, but it often returns harmonics of the true period. So you do need to be careful about the analysis, and you need to experiment with phasing the light curves. You can't just say, oh, well, the computer says this, it must be true. You need to be careful about what the computer is saying and look and make sure that what the computer is saying makes sense. There is a lot of circular analysis and checking. Again, just because the computer says it doesn't mean it's right. It's very easy to be fooled with this kind of analysis. All right, so more broadly, there are a lot of telescopes that are looking and will be looking for things that change in the sky. There's a lot of exoplanet stuff, but there's also things that are looking for explosions. This is where the discovery space is and will be. This is where the data spigots are going to turn on imminently. So this kind of skill is going to be in demand. There are a lot of data. It's not all created equal. There are different strengths and weaknesses of all of these data sets. The space-based light curves are generally more precise than ground-based, but sometimes the ground-based data are better depending on what you're trying to do. And the accuracy of the light curves make a huge difference in what you can do with them. Here's a zoo of light curves of the kinds that you can get from space. This is what the zoo of light curves you get from disked stars with disks around them. You can get some that are plain periodic. This is 2 periods that are beating. Here you get something that you can still see a period, but it's not as clean as that, hence quasi-periodic. You get things like this, where it's sort of trending along and bursting. not periodic though. That we call a burster, and it's probably accreting. Those are probably pops of accretion. Here you get things that are trundling along and then dipping. That is probably accretion columns or other kinds of dust occulting our view of the central object. Here you get a sinusoidal component that is coming from spots on the star, but then the dip is an accretion column rotating into view every orbit, every rotation. Here, stochastic, again, disk stuff, accretion column stuff. It's not periodic. There's not a lot we can do beyond say, oh, yeah, that looks like it's got a disk. And then long time scale variations. Here's examples of light curves of young stars from the ground. There are some things that look very similar, right? Bursty things, dippy things, periodic things. There's lots more noise, but look, it's a much longer time baseline. These are over years rather than 70 days. So approach all of these time series analyses with caution. Do not overinterpret what you're looking at. Test your assumptions. Don't shoot yourself in the foot. Your windowing function can either help or hurt you. The ground-based stuff in particular will tend to have one-day aliases. So no matter what you do with ZTF Assassin or upcoming Rubin, that's going to observe once per day or every few days. And so you're going to end up with a lot of peaks in the power spectrum at a day, half a day, 2 days that aren't going to be real. With Kepler and TESS, those data tend to be once per 30 minutes. Occasionally you get faster than that. WISE, the data tend to be every 90 minutes for few orbits and then nothing for 6 months. So it's got a lot of those big gap data. The photometric precision really matters. The ground-based is really precise. But the ground-based can be precise, but it might not matter if the weather's bad. The space-based can be really precise, but it may not matter if the telescope is breathing for instrumental reasons. The kinds of plots that I make, there are tons of statistics I typically calculate. There's a ton more that I could calculate. For my NITARP teams, I tend to put like a subset of them, the ones that we have found to be more useful. So I talked about most of the more complicated ones earlier. You may find more that you want to add. If you're watching this because you're working on your own, you can go down months of a rabbit hole exploring the stats you can use. I have found that making plots of observing windows is useful. So these are two examples, right, where I've got, this is an arbitrary y-axis, but this is just showing you a dot every time I've got a data point for ZTFR and G and I. I didn't plot the WISE ones there. So this is just showing you, okay, there's not very much I data, but there's a lot of R and G. Here for this target, there's not very much G either, right? There's a lot of R, but not a lot of G or I. But look, that x-axis is 2,000 days of data. So that's 5 years. So this is just a really quick way of absorbing how much data there are in terms of time and wavelength. Here's the plot of some ZTF data. So there's ZTF-R and ZTF-G. Those are error bars. So you can see the error bars in this case are smaller than the point, which it should be. Look at the range there. And then this is color for the matched points. Not every R point has a matched G point. I think in general, I match them if they happen within a day, but that's less than ideal for young stars, but it's all I've got. Yeah. And then here's an example of the time-dependent color magnitude diagram, G versus G minus R. Here's the SED for that. So it's got a disk, and that's consistent with reddening. Here's just some of the statistics: mean, median, skew, kurtosis, mean absolute deviation, min and max, the amplitude between 10 and 90%, the amplitude of the signal of the distribution between 10 and 90%. So that gets rid of the outliers. Zeros is the zero crossing time, meaning the number of times the light curve crosses the mean. Standard deviation, chi-squared, Stetson, if I have matched pairs of observations. M and Q, so the M and Q is something that Anne-Marie Cody designed. So M is talking about up-down symmetry, and Q is talking about periodicity, periodic. M is easy to calculate, Q is harder. So I've calculated in many cases M, but not Q. And then the ZTF color diagram, it's easy to calculate a slope, a best fit slope, and the error on that. And I can calculate the correlation coefficient easily, but in order to calculate the probability that uncorrelated could explain the arrangement of the points, I have to do Monte Carlo simulations, and those take hours to do. And so I don't generally do them unless I need to, because it does take a long time. And then, so some concrete tasks, things you need to do. Do the light curves look okay? Are there single point outliers that don't seem real? Especially if the rejection of that 1 point means that the target is no longer variable. We should get rid of that 1 point. If, especially for the ground-based stuff, if it seems like there's more than one star caught in the aperture, we need to clean that up. So we need to edit the light curves. And if you're working with me, you need to tell me what edits you want so that I can make the edits and rerun everything. And then the issue of whether or not it's periodic did someone else think it was periodic before? Is it periodic in just one band? Is it periodic in color, but not the individual band? Sometimes that happens. I don't know why. That's really cool if it happens. And again, remember, if it's periodic, it is also variable. And you can try to figure out if it makes sense to get a light curve from another source to see if you can have an independent check on the variability. And then if you have more than one color, you can see, oh, is the variability from reddening or from something else? And you can look for the really strange ones that are variable in one band, but not another. And the kinds of science you can do, you can look for what fraction of the targets are variable, what fraction are periodic, what fraction of the variables are consistent or inconsistent with reddening, what fraction of the young stars are variable or periodic, what are the ones that are variable or periodic as a function of whether or not it has IR excess, big IR excess versus smaller IR excess. And if you have enough periods, you can look at the rotation distribution to put it in context with other clusters. Look at the light curve properties of the disk versus non-disk stars. You can look for evidence of recent disk locking. You can look for correlations with X-rays. There's a lot of science you can do once you get done with the basic analysis. But the basic analysis is pretty substantial, and you need to invest some time in it to really do it right.